I would like to talk to you about Object Oriented Geostatistics. Now, this is a project that I have been developing for the last 3 years, or maybe 5 years, under the supervision of Piercesare Secchi. So first, let me thank Eni for the opportunity of being here today for this great recognition of the work. And let me thank the Politecnico di Milano for the opportunity that gave me in the last years. So I would like to give you, so this is the outline of my presentation. I will start with a brief introduction to object-oriented geostatistics and the way in which we understand object-oriented data. Then I will talk about kriging in Hilbert spaces. I will illustrate a case study that really motivated us to go on with this general approach. And I will show you some further examples and extensions of this work to other applications. And I will conclude with some further research. So what do we mean by object data with spatial dependence? Now imagine that we have a spatial domain, like this region of Canada, in which we have some observation at some locations. Now, the locations in this case might be meteorological stations, but they might be wells or some other kinds of spatial locations. At these locations, we may observe functional data, so data that are themselves functions. So we deal with a bunch of functions, of curves, that are spatially dependent because of their locations. For instance, imagine this. These are daily mean temperatures along the year. And so in this case, we might be interested in studying how the temperatures vary in space. Now, another kind of complex data that we might deal with are distribution functions. So these are precipitation distributions that might be collected at this meteorological station. Again, these are functions, but are particular kind of functions. They need to be in 0, 1, so they are constrained functional data. Now we can have more complex data objects like covariance matrices. In fact, these are constrained objects that live in particular spaces, and the properties of these objects need to be accounted for if we want to manage the spatial dependence and to make prediction of this kind of data in a meaningful way. So the idea of the project is to develop a coherent framework, a general framework, to deal with all this kind of data within the same mathematical context. So in general, we will aim to estimate the structural spatial dependence, so how the information at nearby location is correlated, and to use this spatial dependence in order to make predictions at unsampled locations. For instance, here, we might not be able to put a meteorological station, but we might be interested in understanding which is the kind of temperature curve that we can observe, or the precipitation distribution, or the correlation among some physical phenomenon at that point. So the methods that we have developed are those of object-oriented geostatistics. So we use an object-oriented approach. We consider our data as object in mathematical spaces. And we use a geostatistical approach, in a classical sense, I would say, to treat the spatial dependence. But before going on with the methods, why should we use object-oriented geostatistics instead of classical methods? Now, complex data are increasingly available in industrial and engineering case studying. So often the data are high or infinite dimensional. Infinite dimensional data are found every time we measure a function. Now, a function is somehow infinite dimensional because it needs an infinity of point evaluation to be fully characterized. Now, sometimes the data are constrained. We might have positivity constraint, or we might have constraint of distributional data, like the precipitation distribution that I showed before, that needs to be in 0, 1. These are only 2 cases that we have treated This is a case that I will show later on, dealing with an aquifer with some distributions collected within the aquifer. This is a case study dealing with the shale play. So these are wells, and at the wells we have observation of production of gas in time. So these are two cases in which we have complex data, and we need in some way to make prediction of the unobserved data. Now, most of the previous approaches focused on only few of the characteristics of the complex data set and try to characterize only these few characteristics. So imagine that we have this aquifer, we have the curves of this aquifer, then I will be more specific on what they actually represent. But imagine that you have a data set of curves of this kind. Now, we may know that the curves are red or blue. And classically, in fact, what we could have done was to just keep the information about the color of the curve and transfer this information over the entire system. Now, what we want to do is to consider the entire information content in the curve and go to make a prediction of the entire curve over the domain. So for this reason, we use an object-oriented framework in the sense that the atom of the analysis is the entire data, the entire curve, and not only one or two of the characteristics of the curve. So the main idea of the project is that the data are objects within a mathematical space. So we come back to a rather simple case, the case of Euclidean data of 2 dimensions. Now, if we had to deal with data that are vectors of 2 dimensions, we could use a usual Euclidean space, R2, where the points are b-dimensional. Now, in this space, we are able to make operations, and we are able to measure distances, angles, and lengths of vectors. So we can, for instance, make sum of vectors. We can make product by a constant. We can measure the length of the vector through the notion of the norm. This is the usual Euclidean norm. We can measure the distance between 2 vectors, and we can measure the angle between 2 vectors. Now, it turns out that all these properties can be measured once we have definitions of operations and the definition of an inner product or a scalar product. Now, the idea is that for complex data, we have mathematical spaces that have a similar structure, and these are Hilbert spaces. Now, of course, the dimensions are much more than 2, but the idea is the same. So we have vectors, we have points of these spaces that are objects. In our case, will be most of the times function. But we can make the same kind of operations that we did before. So we can do sum of objects, product by a constant. We can measure the length of this vector, so the norm of the function. We can measure the distance between 2 functions, and we can measure angles between functions. Now, and all of this is possible because we have definitions of operations and definition of an inner product that makes the space complete. So now, coming back to our problem, the idea is that we have spatially dependent data. We see the data as objects within a mathematical space, a Hilbert space, and then we try to make a prediction of a point within this space. Now, we will use the geometry of the space to measure the spatial dependence, to look how similar the objects are in terms of how distant they are in the space of objects. And we will make predictions at their sample location doing linear combinations of the data, accounting for their spatial dependence. So this is the idea of the project. Now, let's go to some, not a lot of technical details, but just the mathematical framework. So we assume that our data are a partial observation of a random field that is valued in a space of object, a Hilbert space, with this geometrical structure. So sum, product by a constant, an inner product, and the end-use norm. Now, just to keep the the pictures. So we imagine that there is a surface. In fact, this is should be a surface of objects. We have some observations of these objects, and we want to reconstruct the entire surface. The first idea is to, as I said, to model the spatial dependence. So what we actually do is to give a statistical measure of spatial dependence, that is the trace variogram, that is precisely defined in terms of how different the data are at different locations. So if you're familiar with geostatistics, you will recognize the classical form of the variogram, where instead of having just the modulus, we have the norm. Now, the second idea is the one about prediction. So we want to take weighted average of the data, accounting for the spatial dependence. So we look for a Kriging predictor that is the best linear unbiased predictor, where here we have scalar weights that we need to find, and these are the data. So this is a linear predictor in our Hilbert space. So the problem of Kriging, in fact, is the problem of finding these optimal weights in order to minimize some measure of error. So to minimize the distance in my space, in mean, between what I actually predict and what I would like to predict. And then I have an unbiasedness constraint that ensures that in mean we are right in the prediction. Now this is the main results that allow for all the analysis that I will show from now on. Under some assumptions that are really the same as in classical geostatistics. So in practice, what we do is to decouple the process in a deterministic term that is the mean and the stochastic residual, and then we assume a linear model for the mean. Now, under these two quite intuitive assumptions, we have that the problem of Kriging is well posed, and we can find these optimal weights by solving this linear system, which has the very same form as its classical counterpart, and it has the same dimension of the matrix system that we would get in the scalar case. So we also have the same kind of complexity in solving the problem. Now, why this model, this method is useful for the applications? Well, it's quite flexible. It's flexible because we can choose this Hilbert space in order to represent the data characteristic that we are interested in. And in particular, this space may allow you to account for the differential information of the data, so not only on the pointwise properties, but also on the derivatives of the curve. It can allow to account for data constraints in an elegant and meaningful way, as the case that I will show you in a while, and can also allow to deal with manifold data, Riemannian manifold data, like covariance matrices. Then we have a second source of flexibility, which is this linear model for the drift. Now, this linear model can be a priori known, and in this case, we fall in the usual case of universal Kriging. It can describe covariates collected together with the data. In this case, we are in the case of Kriging with external drift. And it can account for cluster information, so for label for the data. So if we have red and blue curves, we can account for the fact that we have two groups and use this information for making prediction. So we go to the first case study. It is a real case study about a test site, which is an alluvial heterogeneous aquifer in Germany. So we are in the southern part of Germany, near the city of Tübingen. This is the research site, and this is the river Neckar that makes a bend, and this is our aquifer. So this is the Neckar River again. Here we have 12 wells, and for the moment we focus on one well, which is the well B5. Now, along the well B5, we have some observations, and in particular, we consider the observations of particle size distributions. Now, particle size distributions are cumulative distribution functions that describes the distribution of grain sizes within a soil sample. So these are cumulative distribution functions, as I said. They are in 0, 1. And in fact, what we have is a collection of these curves along the well. So now the space is in this direction is a one-dimensional spatial domain. And here for each point, each of these 60 points, we have a curve, which is constrained. So our data object now is this cumulative distribution function. Now, our idea was, OK, so these, in fact, are some kind of observation from a cumulative distribution function that we assume to be continuous. So we first smoothed the data, and then we focused on their densities that are peculiar kind of constrained functional data. And so the idea was to choose, accordingly, the Hilbert space embedding for our data. Now, to choose the Hilbert space, we have to look into the properties of the data. Now, I don't want to go too much into the details, but just to say that the peculiar kind of constraints, so this data needs to be positive and to integrate to a constant, so they can be seen as compositional data in the infinite dimensional setting. Now, in practice, what is possible to do is to define operations and inner products in order to be consistent with the kind of data constraints that we have. So in practice, we use a log ratio approach, and the geometry that was introduced in 2006 by Egosue and co-authors. Now, I don't want to focus on the kind of operations, but just to say that we have a sum, we have a product by a constant, we have an inner product, and so we have our mathematical space where we can see our data and we can make operations among the data. And once we have this kind of embedding, we are able to estimate the structural spatial dependence, so to estimate this curve, which is the variogram, that describes how data at different legs are correlated. And on this basis, we are able to make prediction at the unsampled locations. These predictions are useful in field studies. They can be used for global quantile assessment, meaning that once we predict the entire distribution function, we are able to predict jointly all the quantiles of the distribution. And they can also be used for hydrofaces characterizations in Monte Carlo simulations. Now, just to show you briefly how can we use this prediction for classical things, classical goals of hydrogeological studies. So in this case, we aim to compute the log conductivities by employing classical formulation, so the Kozeny-Karman equation and the Hazen equation. So these equations are in fact based on some parameters, but mostly on D60 and D10 that are the quantiles 10 and 60 of the particle size distribution. Of course, since we have predicted the entire distribution, we have for free these two quantiles. So what we have done was to apply our method, object-oriented kriging in blue, to make prediction of D10 and D60. And then we have computed the hydraulic log conductivity according to the Kozeny-Karman equation and the Hazen equation. Now you will see that the results are consistent in the two cases. So the red line is based on a classical method, a classical kriging method in 2 dimensions, while our case is the one of object-oriented kriging, and it is in blue. Now in this case, the results are consistent, but in fact, we are not guaranteeing that using a 2-dimensional kriging, the ordering relations between the D10 and the D60 is respected, because we are not imposing that D10 is lower than D60. So one big advantage of our approach is the fact that we are able to guarantee that as long as we use the entire information content within the particle size curve, then we can get consistent estimations of all the quantiles jointly. Now, some other examples of applications. In fact, this is the extensions to the three-dimensional case of our study on particle size data. In this case, we need to account for the fact that there are different soil types within the system. So you see we have 3 different soil types, red, blue, and yellow. And we can incorporate this information in our creaking predictor through the drift term and get a prediction of the entire system. Another kind of application that we have studied is the one concerning production rate curves in unconventional reservoirs. So in this case, we were in the US, this is Texas, and we studied a shale play here. This is the kind of production that we got at that shale play. So these dots are the raw data. We smoothed the data, and again, we have to deal with the data set of production rate curves that are functions. So what we did was to interpolate the functions over all the domain, and what we got was a series of these maps along time. So these are slices of the complete prediction that we got at that field site that can be useful to understand where the production may be higher and where the production may be lower. Another kind of application that we dealt with is with climatic data on associations. In particular, we worked with covariance matrices between temperature and precipitation. We had a bunch of data in the Canadian region that I showed at the beginning. And the aim there was, again, to interpolate the data and to understand which is the association between these 2 phenomena at unsampled locations in the system. Now, these data are particularly complex. They live in Riemannian manifolds that can be figured as curve space that can be locally approximated by a Hilbert space. So in each point of this curve space, we have a Hilbert space that approximates the data. And so we can map the data from this curve space to the tangent space, solve the problem in the tangent space, and then come back to the manifold. And now in the tangent space, we have all the machinery to make the analysis. And so the problem can be solved. Now, this kind of analysis might be useful also for other kind of Riemannian data, like permeability tensors in anisotropic media and diffusion MRI, where we have diffusion tensors. Another application which is a bit different from the ones that I showed before is the one to meta-modeling. Now, in this case, we don't deal with the physical space, but with a space of inputs. Imagine that we have a very expensive numerical model that may approximate a system of PDE. We have an input that provides an output, which is complex, like this function. So if we could simulate this system for lots of inputs, we could characterize completely the kind of output that we can get. But in fact, since this is expensive, we can simulate it only for few points in the input space. So in this case, I just plotted the 2-dimensional parameter space. So each point is a point where we have run the numerical model and we got an output. So this is the output, this is the input that we use. Now the idea is that if we cannot simulate for all the input space, we can choose some input points and then we can interpolate the outputs over the input space. And we can do that with very simple, with very complex responses in a very efficient way. Now, to conclude, in this project, we have introduced object-oriented geostatistics. It can be applied in any Hilbert space. It allowed to estimate the structural spatial dependence and to make prediction. For the very first time, it allowed to properly capture all the critical features of the data to account for possible data constraints, as I showed you in the case study on particle size data. It allows to incorporate secondary information available at the field site. And it allows to provide solutions in an efficient way at the same cost that you would have with very simple data. Now, some other kind of research that we can do, starting from this, is about uncertainty quantification. So to give some idea of the uncertainty that is associated to the prediction, for instance, this is a geostatistical conditional simulation that is, basically it is a realization of the random field that is coherent with the data. So it is something that we could have observed if we had drilled here. So it is not the Kriging prediction, but it is something that is likely and is consistent with the data. So for instance, we could use the statistical simulation to characterize how uncertain our predictions are. And this is something that you see here. For instance, in black, this is the Kriging prediction for this depth, which is here, near the data. And this is a bunch of curves that were simulated through geostatistical conditional simulations. Now, far from the data, here, we have a very similar prediction. We are more or less here. But you see that the bunch of curves are much more fluctuating and much more different. So you see that the uncertainty here is much higher than the uncertainty here because we are much more far from the data. Now, this is one kind of uncertainty in quantification, but of course, this opens a broad field of research that will be interesting to study in the years. Now, other kind of analyses are those based on the idea of creating optimal spatial designs or going through in the direction of complex data with complex domain, like in these pictures where we have, for instance, estuaries, or we have data over some very complex domains with river inside, and here characterizing the spatial dependence and making prediction is something highly complex. So before ending, let me thank again Eni and Fondazione Eni Enrico Mattei for the award and for the experience that has been this ceremony. Let me thank MOX and the statistics group at MOX, the Department of Mathematics and the Politecnico di Milano, and let me share this big recognition with my co-authors, and in particular with Piercesare Secchi, who has been really a great guide in this year. Thank you.